Hello and welcome to this video lesson. In this video we will be analyzing a circuit with multiple batteries. We have a circuit here with multiple cells and resistors. So we got a cell over here, 2 volts, 15 volts, 12 volts, and we got multiple resistors. Resistor 1 at 1 ohm, 2 at 5, 3 at 2, and resistor 4 at 3 ohms. And we want to figure out the following information. So we want all the informations that we can get. We want the voltage or potential differences across each resistor and each battery. We want the current across them, and we want the power. We already have all the information on the resistors, so we're going to start off by writing those down. So resistor 1 or location 1 has a resistance of 1. Resistor 2 has resistance of 5. 3 has 2, 4 has 3, and we're going to assume that there's no internal resistance in these batteries, so I'm just going to remove these. And I know the potential differences across the batteries here. So the EMFs here, E1. So the way I'm going to label these actually is I have resistance 1, which is closest to this battery, so I'm going to call this EMF 1. And then I have resistance 2 here, which is closest to this battery, so I'm going to call this EMF 2. And this one I'm going to call EMF 3. And their values are going to be 2, 15, and 12. Now I have included all the informations that I do know at the moment. And I can't solve for anything because I don't have enough information to solve for anything else. Usually I need 2 pieces of information to find something else. In order to figure everything else, I have to start using the Kirchhoff's laws. So I'm going to start off by Kirchhoff's voltage law first. Kirchhoff's voltage law says that if you have a coulomb of charge that moves through a battery, it gains certain amount of energy. And as it moves through resistors, it loses those energy. Now, if it's going in the same direction as the battery, so if it's a negative charge coming towards the positive and being pushed from the negative side, it gains energy. And if it goes in the opposite direction, so if it's being pushed away from this terminal, then it's not going to be gaining energy. So we have to use a negative value there. So I'll show you that as we create the loops. So let's just do that. Let's start creating a few loops. I'm going to create one loop over here, and I'm going to call this loop loop A. And I'm going to create another one, and it doesn't really matter how you create it. You can actually create another one going all the way back like this, or all the way on the outside, or you can draw one on the inside. So I'll draw one in the inside, and I am kind of saying the loop is going like this. So the current, I'm kind of assuming that it's going upwards here. So I'm going to make the same assumption. So for my loop on this side, I'm going to draw it counterclockwise so that the current going through this wire over here is actually going upwards. You can do it in other ways. It's just easier this way. So I'm going to go in this direction, and I'm going to call this loop B. You could have chosen your loop A to go this way and loop B to go the other way. It doesn't really matter which directions you choose your loops to go. You just need to make sure that your loop includes the path of 1 unit of charge. So in this case, in my loop A, the charge is going in this direction, and in loop B, the charge is going in this direction. Now that I have this, I'm also going to include my currents, and I'm going to give it some values. So I'm going to go ahead and assume that current 1 or I1, which is the same for resistance 1, this battery over here, or this cell, and this resistor, because all of these are in the same wire, so they have the same amount of charge that's passing through the cross-sectional area per unit time. So I'm going to say all of this is I1, and I'm matching it with this and this. I could have also called it I4, doesn't really make a huge difference. I3, because my loop is going clockwise like this, I'm gonna call this I3. And because both of my loops for this wire are pointing upwards, I'm going to choose this direction to be my positive direction. Now, later on when we analyze it, if we get a positive value for our current, it means that it is moving in this direction. If we get a negative one, it means it's actually moving in the opposite direction. So we'll see what we will get when we find our values. Let's start with Kirchhoff's voltage law for loop A. And Kirchhoff's law states that as a unit of charge moves through a loop, the total amount of energy that it gains is equal to the total amount of energy that it loses. So the total amount, let's kind of imagine that we have an electron here. And this electron is kind of pulled towards the positive terminal and pushed away from the negative terminal, meaning that it's going to gain some energy here. So I'm going to use that as a positive value. That's the EMF. It's going to go, 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 go. It's going to lose some here. I'm going to write it when I'm writing the right side of the equation. It's going to go, 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 and then it's going to go through another battery over here. But this time, it's being pushed away from the negative side and pulled towards this direction. So this cell is actually pushing it in the opposite direction. So I can't use a positive value. I have to use a negative value here. So I'm going to go negative 15. And it's going to go, 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 go. It's going to come back. I'm just following the loop. There's no more batteries, so this side of the equation is already complete. I'm going to go and write all the potential differences across the batteries. So I'm going to keep following it. It's going to come, 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 come. And here, it's going to lose some energy. So this is going to be the first V. I'm going to call this V4. Plus, it's going to go, 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 go. It's going to go here, and we have R2 here. And note that this is actually a nice case in which our loop is following the same direction as our current. If it's not, you would have to use a negative value when you're plugging some of the next step. But for now, we're just going to go. We know that we're going to lose some energy in resistor 2, and then we're going to lose some energy in resistor 1. Now, for the next step, we are going to turn our voltages or potential differences to I times R. So on the left-hand side, 2 plus negative 15 is just negative 13, so I'll leave it like this. For V4, I'm going through this loop here, and I now have to look at my current and my resistor. So the current that's coming here is I1. I1 is moving in the same direction as my loop, so I have to use a positive value for it. So I'm going to do positive I1. And it's going through resistor 4. So this is going to be R4. And you can write it as R4. I'm just going to write it as 3 because the value of this resistance is 3. And then it's going to go, 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 go. We've already taken care of this. And then it goes through resistor 2, which is 5 ohms. And current 2. So I have to multiply I2 by R2 here. And the direction that I'm assuming that the electrons are going is the same direction as I chose my I2. So I can just use a positive value here. So this is I2 times 5, 5 being the resistance 2, plus, it's going to keep going, and for voltage 1, my current is going in this direction, so that's I1. My loop is also assuming that current is going the same direction, so I can use a positive value. And that's going to be I1 times 1. I can now simplify this as negative 13 is equal to, I have 3i1, 1i1, so they add up to 4i1 plus 5i2. I've now taken care of my loop A. Let's do loop B. And we're going to follow the exact same procedure. So I'm going to go total EMF is equal to the total voltage lost. I'm going to do this one a little bit quicker. We're going to start off, we're assuming that our loop is going in this direction. So I'm going to kind of take an electron and say that it starts right here. And when it goes through this battery, it's going the same direction as it should. So it's attracted to the positive terminal and pushed away from the negative terminal. So it gains energy here. So that's going to be 12. And then when it goes, it's going to come here. Now it's being pushed away from this terminal and pulled from this one. So it's opposite. So if this was the other way, we would add. But since it's actually being pushed away from this side, we have to subtract. So this is negative 15, and this is going to equal 2. There is no more batteries here, so I've taken care of the left-hand side. For the right-hand side, I have to look at the voltages. So it goes through resistor 2, and it goes through resistor 3. So I'm just going to write V2 plus V3. Now I will simplify the left-hand side. That's negative 3 is equal to, for V2, I'm assuming that my current is moving upwards in this wire, and I2 is also in the same direction, so I'm going to use a positive I2, and my resistor here is 5, so this is going to be I2 times 5, and plus, for V3, I'm assuming that I3 is going in this direction, and in terms of my loop is the same idea, so I can use a positive value of current here, and that's going through this resistor. So V3 is equal to I3 times R3, and I3 we don't know, but we do know R3, its value is 2. So I can just simplify this and write it as negative 3 is equal to 5I2 plus 2I3. Now I have two sets of equations, so I'm going to write them down here. I'm going to write the first one like this, 4I1 plus 5I2. I also need I3, but I don't know its value. And for my first equation, I'm writing the purple one down here. I don't have any, so I'll write it as 0I3 is equal to negative 13. Now I'm going to write the pink one. The pink one goes, there's no I1 in this equation over here. So 0I1 plus 5I2 plus 2I3 is equal to negative 3. Note that I have two equations, but I have three unknowns. I don't know what I1 is, I don't know what I2 is, and I don't know what I3 is. So I need one other equation in order to solve this mathematically. And I've already chose two sets of loop here, and I've already used Kirchhoff's voltage law. So I now have to use Kirchhoff's current law. And to do that, I need a junction. I need to choose a junction. And I'm going to choose the junction right at this point over here. And I'm doing that just because, well, there's only two junctions, this one and this one. They will yield the exact same equation because you have the same currents coming in and out, I2, I3, and I1. But since I've pointed everything down here, it's a little bit easier to kind of show. So I'll use this, and I'll write this as junction 1 or node 1. And I'll write at junction 1, the total current going in needs to equal to the total current coming out. So looking at this junction over here, the current that goes in is I2, and the currents that are coming out of this node or junction are I1 and I3. So I'll write it as I1 plus I3. And this is my equation. I'm just going to rearrange it so that it is in this form. So I have all the I1s aligned with each other, I2s with each other, I3s with each other, and the constants on this side. So if I rearrange this equation, I will get I1, and I have one of them, minus I2, so I have to subtract I2 from both sides, and I get minus I2 or minus 1 I2. And if you want, you can actually write these as ones. Not necessary, but you can. Plus I3, and I have one of them as well, is equal to 0. So basically all I did is I subtracted 2 from both sides to get it here, and on this side now I have 0. Once you're at this point, you've done the hard part of the question. The rest is going to be quite easy. So you have 3 equations and 3 unknowns, and at this point over here, I usually have my students use their calculator to solve this. And you can also just use simultaneous equations. You have 3 knowns and 3 unknowns, but we're not going to go through that process. That's more math than it is physics. So what I want you folks to do is just grab a online calculator, maybe if you don't have, if your calculator doesn't do it, and look at a 3x3 system of equation solver. And once you have this, you can treat all of these as variable x, all of these as variable y, and all of these as variable z. And then just plug in the coefficients. Coefficient of x is 4, y is 5, z is 0, constant is negative 13. And you're going to do that 3 times. And once you have that, the calculator will show you the final values. And in this case, using scientific calculator, I1, I2, and I3 will equal negative 2, negative 1, and positive 1. Okay, now what does this mean? We have an I1 value which is negative, so we were assuming that I1 is going to be going in this direction. What we got is a value which was negative, meaning that no, our initial assumption was actually incorrect. I1 will not be going in the left direction here, or it's not going counterclockwise. It will actually be going clockwise. Let's see if this makes sense. Within this loop over here, you have 2 sets of cells. One is 2 volts and one is 15 volts. This is much weaker than this one in terms of providing a potential difference. So if this is pushing electrons with an energy of, let's say, 2 joules per coulomb, and this one is pushing it in this direction with 15 joules per coulomb, the total force that you will get in this loop will very likely be in this direction, because you get a stronger cell pushing the electrons in this direction compared to this one. So it makes sense that the current should actually be going in this direction. Now, did we do anything wrong? We didn't. So we got all the values that are correct. We just made an assumption initially that was incorrect in terms of direction. Our magnitudes should work if we do everything correctly. And in this case, we did. And yeah, the current in this direction will be 2 amps, and it will be going in this direction. So even though this battery is pushing in this direction, current across it will actually be going in the opposite way. Now, looking at this loop over here, we said that I3 is going to be 1 amp. So I3 is actually going in this direction because it's in the same direction that we assumed. It's 1. And I2, we assume that it's going upwards, but it's actually going downwards because we got a negative value. So since we got negative, it means that the current in this wire, in I1, instead of going in this direction, is actually going in this direction. So maybe I'll use red to kind of show the actual movement. So this is going in this direction at 2 amps. This one is actually going in this direction at 1 amp. And I3 is going in the proper direction that we initially assumed at 1 amp also. And this kind of makes sense. We got a very strong battery here, which is pushing things in this direction. So that's coming in at 1. I3, this is also a very strong battery, so it's pushing everything down in this direction. And even though we have a battery here that's pushing in a current in this direction, it's just not strong enough. So these two will push the current and push it through this wire. So one is coming down here, one is coming down here, and they add up to 2 and they move in this direction. And then that's the proper directions that current is flowing. But since we have I1 here, I3 here, and I2 here, and we got these values for it, and these are negative, just looking at them, we know that we can kind of conclude which directions those currents are going without having to rewrite it with the 2, 1, and 1 like this. And now that we have the currents, everything else is going to be much easier. So I'm going to write the absolute values here. So we're going to have 2, we're going to have 1, and we're going to have 1. And since you already have shown the negatives here, you're okay. You can include the positives here. To find the voltage, we just multiply current and resistance. So 2 times 1 is 2, 1 times 5 is 5, 1 times 2 is 2. And the current across here, 4 and 1 are the same because it's the same wire over here. So the current across all of this wire has to be the same. Remember that there are many, many electrons here. And if there's a small push, it's just like a lineup of people. And if there's a little bit of a push here, that push is instantly happening in this direction as well. You can also think about it in the other direction. So this is also going to be same as I1, which is 2. And 2 times 3 gives us 6. In terms of the current that's going across the batteries, this is same as I1, so that's going to be 2. Current going across this is same as the current going across this wire is all the same, so I2 is going to equal to 1, and I3 is going to equal to 1 as well because the current across all of this wire is going to be the same. Now you have to calculate the powers, and to calculate the powers, you multiply the potential difference times the current. 2 times 2 is 4. 5 times 1 is 5. 2 times 1 is 2. 6 times 2 is 12. 2 times 2 is 4. 15 and 12. Now, you may also ask, why would we ever have a situation like this in which the current is going into a battery? And well, the reason for that is because we want to charge the battery. And in this particular case, within this system, we can provide 2 amp in this direction. So we can push the current into the battery in order to charge it. And note that these two batteries are kind of providing the energy here. And this battery is actually taking it. So this could be your smartphone or any other device that you're using, and these two batteries are providing the energies. So even if you look at the power, you get the 15 plus 12 here, which add up to 27. And if you add all of the energies that are actually being used, you got the 5 9, 11, 23, and 27. So all of these are actually taking energy, and these two are actually providing the energy in this particular case. So a very quick summary of solving questions with multiple cells. Usually if you have multiple cells that are connected in parallel, so if you have them in series, you can just add them up. It's not a problem. But if you have them in parallel, what you want to do is you want to use Kirchhoff's laws because it's much harder to find a proper equivalent resistance. And what you would do is you would pick a few loops. And in this case, I've taken this loop over here and this loop over here. You can also use this loop over here and this loop over here. It's completely up to you. And that's for the voltage law, and you can use Kirchhoff's law for current as well. Just take a junction. In this case, we only have two junctions, so you have to just choose one because the equations for both are going to be exactly the same. You have the same currents coming into those junctions and same ones going out. And by that I mean you're dealing with only I1 and I2 and I3 for both junctions, so they would give you the same equation in this case. And once you have that, you're going to have a system of equation. It could be 2 by 2, it could be 3 by 3, it could be 4 by 4, it could be 7 by 7 in a more complex circuit. And then you would use, usually once you have it at that point, you will just use the skills you have learned to solve simultaneous equations if your teachers want you to do it mathematically. Usually for my class, I usually prefer students to, if they don't have a calculator, that can solve this, to just have this as the final solution. And if they do have a calculator that can solve it, I want the actual answers like this. And then the rest of it is just, it's much easier because you can always calculate voltage using current or potential difference by current multiplied by resistance. And sometimes we write potential difference like this as well. It all depends. I'm using the IB format here where we don't include the delta, but in most cases, including delta is the proper way. And we find power by the equation I times V. We can also use other equations for it, but once we have these two, it's just easy to multiply them out. Alright folks, I hope that this was a helpful video in giving you an idea about how to solve circuits with multiple cells, especially when they're connected in parallel. Have a fantastic day.